You're welcome to Maths 101. We're continuing with the next chapter, and that's complex numbers. Okay, so we're now in chapter 6, and the topic is we'll be considering include complex numbers as an extension to real numbers, properties of complex numbers. So you see that all through the video. So we begin with definitions and basic identities you need to know. So we have here what a complex number is precisely. So if you have x and y that are real numbers, I believe you know what real numbers are, then the ordered pair of this form of real numbers is called a complex number. If z denotes a complex number, xy, then we can write it in this form. So that's most times you're used to seeing it as x plus iy. Okay, that's a complex number. So where the real numbers x and y are called the real and imaginary parts respectively. So this is how you denote the real and then the imaginary part. Okay, so basically the side where there's the y is the imaginary part, the part where there's the x is the real part. Okay, so you're used to seeing the z equal to x plus I y. Okay, so that's what you're used to seeing, the real part, the imaginary part. Okay, so the other thing you need to know is that if the real part of a complex number is 0, and it looks something like this, then the complex number is said to be purely imaginary. For instance, you have 0, 5. You can see that the y part of it is 5. So it's purely imaginary. And if the imaginary part of a complex number z is 0, then we write it this way. So the y part is 0. You see there's a value there, the real part. Okay, so we say the complex number is real. Okay, the next thing you need to know is what we call equality of complex numbers. So two complex numbers are said to be equal. So you have two complex numbers, z1 and z2. You can see we denoted them uniquely differently. The entries are different. So they're said to be equal, that is z1 equal to z2, if and only if their component parts are equal. That is x1 equal to x2 and y1 equal to y2. That's when they are said to be equal. Now, having known a little about complex numbers, how do you add them together? How do you multiply them? That's what we're going to be looking at next. So if you happen to have two complex numbers, z1 and z2 of this form, as we've seen earlier, then if you want to sum them together, you simply do this. z1 plus z2. So you add the terms in the real part together, x1 and x2, as you can see here, x1 plus x2, and the part of the imaginary term together, which is c as y1 plus y2. So if it happens to be in the form z1 equal to x1 plus I y1 and z2, which is actually what it is, just not written that way, z2 plus I y2. You want to sum these two together, you simply sum x1 plus x2 and sum y1 plus y2 to get what you see right here. Okay, so that's what you have there. Okay, so now you know how to sum the terms together. What if you want to subtract them? And to subtract the two complex numbers, what do you do? So subtract them, you have here, given any two complex numbers, you have z minus 1. We define the additive inverse. The subtraction is quite easy. I think I jumped one before starting with sum, so let's finish the product part. So I jumped that. Let's do the product. So the product, you multiply the z1 and z2 using this rule. So you do x1 times x2, the components x1 and x2, minus y1, y2, then comma x1, y2 plus y1, x2, meaning that if it takes the form that I'd written before, that is z1 equal to, z1 equal to x1 plus iy1, and z2 equals to x2 plus iy2, you get this value here. Okay, so you can try it on your own, write it out and see if you multiply, you get this value here using this rule. Okay, so like I was saying, for subtraction, given complex numbers of this one, so the additive inverse of this one, which will give you 0, is actually this term here. Okay, so the additive inverse, when you add this to this, you should get 0. That's what we call an additive inverse of the complex number. Now, complex numbers also satisfy the commutative law. How do we mean? Saying that if you add z1 plus z2, it's the same as taking z2 plus z1. In fact, for multiplication, you can also do the same. You can do z1 times z2 and do z2 times z1 to give you the same value. So they satisfy the commutative law. That's complex numbers. It also satisfies the associative law, in the sense that if you add z1 plus, if you have 3 complex numbers and you add the z1 plus z2 and later then add z3, it will still be the same thing as adding z2 plus z3 and then finally adding z1. It's still the same thing. So same also for multiplication. If you decide to multiply z1 and z2 first before you multiply z3 with it, it will still be the same as z1 multiplying z2 and z3, which had been multiplied earlier on. So it is commutative. Okay. The next thing you need to know is what we call complex conjugate. So when we say conjugation, so the conjugate of this complex number is this one you see here. Okay, that's its conjugate. So we denote it z bar. Okay, it's called the complex conjugate. Note, it's different from the difference. That's a subtraction here. The additive inverse is different. The additive inverse, as you can see here, look at it carefully. You can see that it has minus in front of the x and between x and y there. Okay, so it's called additive inverse. It's different from the conjugate. For the conjugate, you have it at x bar equal to x minus I y. Okay, so it's a complex conjugate. It's different. Okay. The next thing you need to know is that if you multiply the complex number and its conjugate, that is always real. You can verify that yourself. So when you multiply, you should get this value x squared plus y squared, which is real because all of them, there's no imaginary part in it. Okay, so then z is given whenever z is given as that. Moreover, you will see us apply some, you will see us do some examples later, but this is always true, that when you multiply the complex number and its conjugate, it will always be real, and this is the value you will get. Okay. Now, if you're told to find the modulus of a complex number, meaning you should find this value. Okay, that's what they mean by modulus. The modulus of z is what you see on the screen, the square root of z times its complex conjugate, okay, which is square root of x squared plus y squared, and it is denoted as the absolute value of z. Okay, so this is a formula which you need to know. Okay, the same thing. So it's either you know it up to here and know that once you see a square root, it's simply saying everything raised by half. Okay, so there's a formula for finding modulus. You're told to find the modulus of a given complex number. So geometrically, the modulus is the distance between the point x, y and the origin. Okay, that's geometrically if you want to see it in pictorial form. So the modulus of a complex number is the distance between the point x, y and the origin, or it is called the length of the vector representing z. the length of the vector representing z. Now, complex numbers z, they correspond to points lying on a circle z0. So once you have a complex number, it actually corresponds to a point that's lying on the circle with the center z0 and radius r. Okay, so every complex number of any form you have is always corresponding to a circle, to a point, okay, lying on a circle whose center is z0 and its radius is r. Okay, always. And what is that formula? It satisfies an equation of this form. Let me clean all my scribbles. So it always satisfies this equation here. So every complex number corresponds to a point on a circle with center z0 with radius r. So it always satisfies this equation. So this is practically the equation of the circle. So most times we want you to know up to this point, but then you note that z0 is the same as what you see in this bracket here. Okay, z0 is just x0 plus iy0. Okay, so that's why I said I've written it there where z0 is equal to x0 plus iy0. Okay, for any non-zero complex number, so you have this complex number, there is a number called z inverse such that if you multiply the two of them, it equals to 1. This number, z inverse, is called the multiplicative inverse of z. Remember you saw an additive inverse earlier on. Let's look at it again. We saw an additive inverse. Where did we see it? Good, there it is. We saw an additive inverse before. So we saw an additive inverse. This is an additive inverse of that complex number. Next, you also saw the conjugate. Okay, you saw the conjugate, which is this one here, complex conjugate. Here, now you're being told that there's something called a multiplicative inverse. The multiplicative inverse will give you, when you multiply it, 1. Okay, so let's not forget that. Let's move on now. More information you need to know is that complex numbers can be represented in a polar form. So that's why we're taking the polar representation of complex numbers. So now we know that every complex number, let's go back, corresponds to a point. Let me clean that so you can see what we know. We know that every complex number corresponds to a point lying on a circle with center, a unit circle with center z0 and radius r. Now we want to see how we can represent it in polar form. So we have r and theta. Let them be the polar coordinate of the point xy, corresponding to the complex number this. Okay, so this is because we know x is of the form r cos theta and y is of the form r sine theta. It's a standard rule, so you should always remember that. Okay, then if that is the case, we can write z to be what you see here. How did they get that? You know that z is equal to x plus I, y. And now you know, if we're using this as our point, polar coordinates, that our x is r cos theta and y is r sine theta. So if that is the case, if you see r is common to both of them, you can factor out r. You'll be left with cos theta plus I sine theta. So that's how we got this term here. So in polar form, z is this. So if you're asked what is the polar form of a complex number, the polar form is what I have put in the box. So if asked what is the polar form of a complex number, given that r, theta, and r and theta are polar coordinates of the point xy, then you say that z is equal to what you see on the screen. Now, the next thing you need to know is the number or angle theta is called the argument. So whenever you see theta, when it comes to a complex number, we call it argument. Another name for it is amplitude of the complex number z. And this theta, if you're told find theta, it is simply theta equals to tan inverse of y over x. So if you know your if you know z theta to be equal to, say, 2 plus I 3. Okay, let me write that again so we know what tan is. So you're told to find if you're told to find the argument of the complex number. I want to write something. You're told to find the argument of a complex number, says z equal to 2 plus 3i. Note, have you seen I've changed it? Now, this is the imaginary part, this is the real part. You're told to find the argument. What are you looking for? You know you're looking for theta equal to tan inverse, because that's what the formula says here. Tan inverse. And what's y? Y is 3. I put 3. And what is my x? X is 2. So you're looking for tan inverse of 3 over 2. So you can use your table, your 4-figure table, and get to your final answer. Okay, so that's how you find the argument of a given complex number. Okay, let's move forward. Now, the next thing you need to know is that the argument is not unique. It says the argument of z, it's theta. And you remember in class previously we had done the cast. We said cast. And we saw something that sometimes you could go several times around the circle, especially when we learned that theta doesn't change if you add 360 or you subtract 360 from it. Okay, so with that knowledge, you know that now if I'm talking about a point on the circle, the angle could change too. Is that not so? It could go bigger than that, than what you're seeing there. So that's why we're saying the argument is not unique, since the argument of z is theta, which is plus 2 pi n, where n is a change in value. If you remember, I told us that you could write it as theta plus n 360 or theta minus n 360. Okay, so because of the value n, whether we're going positively or going negatively, the value of the argument z is not unique. Okay, so that's what we have. So theta will lie within minus theta and theta, and this is called the principal value, denoted ag z. Okay, the next thing is, aside from polar representation, there's another way you can represent complex numbers. That's in exponential form. How do we mean by exponential form? That brings you to what we call the Euler's formula. Now, the Euler's formula is basically this equation you see here. We can write it in exponential form because it's this exponential I theta you can see here. So we can write in exponential form because Euler's formula basically says cos theta plus I sine theta is same as e raised to power I theta. But we know already from the polar representation form that z theta is same as z is same as r into cos theta plus I sine theta. We had proven that earlier on. Okay, so now just watch this. Now you know all of this. This is Euler's formula, see it here. Okay, so and it's the same thing here. So wherever I see cos theta plus I sine theta, I put ei theta. So it means that my z is same as r times ei theta. And that's all. That's the exponential representation of complex numbers. Okay, so this is the exponential form. Okay, so that's how we got that value. They're using Euler's formula, so don't forget that Euler's formula. So now you know how to represent complex numbers in their polar form and also represent them in the exponential form. Okay, That's what you've done right here. Let me take my pen. Right here, which is what I just proved. And you know what this is. It's the Euler's formula. Just pronunciation was given to you. They had to pronounce it, okay? Now we begin with some examples. So you're told to evaluate the following sums. Oh, well, we have two sums. Oh, this is different. Not something's wrong with the font there. Not following, just this one. You have to do this. In your notes, you'll see more examples in your lecture notes. So we want to evaluate the sum of this. So how do we evaluate that? So you know that if you happen to have two complex numbers, let's see if you can find it. Let's see if you can find the sum for complex numbers. There you are. I think right here, good. So if you want to find the sum, you take the z1 and z2, you add x1 plus x2 and y1 plus y2. That's what we said we'll do, okay? So now we want to do the first example. So in the first example now, we have that we're to find the sum of these two terms. So what happens? We're going to have to add, so this is z1 here, because you can see it's a complete complex number. It has x and the imaginary part. This one too has x and its imaginary part. You can see two i's as an imaginary part, and this one I is its imaginary part. So we add 3, the real part, and 1 together. Then we add, whenever there's no number there, though it is I, there's 1 hiding at the side. It's not just written. So we add 1i plus 2i. So that's what we did here. So let's see the solution. So we brought the first complex number and the second complex number. We added the real part, 3 plus 1, which is 3 plus 1 here. And we added the imaginary part. Though there is no 1 here, like I said before, the 1 is just beside the I, do not written out. So we added the real part, which is 1 plus 2. 1 plus 2, and then the I is just outside because it's common to both of them. They're the imaginary part. So what's 3 plus 1? 3 plus 1 is 4, and 1 plus 2 is 3. So that's how we got 3i that you see there. So whenever you're given two complex numbers, you add the real parts, you add the imaginary part, and you're through. For more examples on the sums, you can refer to your lecture notes and try them. You can discuss that online on the WhatsApp or when we meet in class. Next is we're told to evaluate the difference. This is difference, not this sign, this symbol in the middle is F, double F, difference. Let's find the difference, subtract. Like you know in secondary school you did that. Similar to what you did when you were adding, now you're going to be subtracting. So you subtract the first two real terms and then the imaginary terms. Okay, now watch for the y part. Okay, so let's see what we've done here. So we have 2 minus 3i, and we have minus 1 plus 2i. So we're taking the differences. So we want to carefully open the bracket. Okay, the minus sign will go in. So let's see. I didn't write a step here, so let's do it together. So I have 2. I want to open the bracket, minus 3i. Minus times 1 is going to give me minus 1. I'm opening the bracket. Minus times plus is minus 2i. Okay. Again, just like we did when we were solving the example number 1 here, we'll do same here. So we add the real parts together. I have 2 naira. I'm owing 1 naira. So we bring them together, and you see them together. I'm owing 3 imaginaries and I'm owing 2 imaginaries. I bring them together. You see that? So 2 minus 1 is 1. I'm owing 3 i's and I'm owing 2 i's. I definitely will be owing 5 i's. That's how we got the value you have there. Okay, you can go back, play slowly, and see if you can understand. Again, there are more examples in your lecture notes. The next example is the product. We want to multiply, okay? Similar to what you did before, and they said after multiplying them, so we have to evaluate this, and afterwards you have to evaluate this, okay? Basically, you're going to be studying to this one to determine this. So let's see. So let's see how we're going to multiply this. So we wrote them out, so it's it here, same. In the same way you will multiply if you happen to have A plus B. Let me see, let's choose numbers, let's choose values. The way you would have done if you had 3 plus A into, say, 1 plus A. What do you normally do? You take the 3 to multiply all of this, is that not so? Then take the 2 and multiply again all of this. Sorry, take the A and multiply all of this. In the same way, similar approach. So let's see us do it. Okay. So now we have 3 minus 4i, and it's multiplying 3 plus 4i. Can we see how we can multiply that? So we take the 3 first, the 3 in front here. That 3 will go into, it's multiplying the one with the positive term, plus 4i. And then the minus 4i is multiplying 3 plus 4i. Okay, so that's how we got that step. I didn't show that step. So now what do you do? 3 times 3, this side, 3, we get 3 times 3 as our next step, plus 3 times 4i, 3 times 4i. Now minus times, there's no sign here, so that's minus this, minus times plus. So 4 times 3 is going to give me what? So I'm doing 4i times 3. Now another minus times plus is minus. Is that not so? So 4i times 4i. So that's how I got what you see right here. Okay, what you see on the board there. I just didn't write this step for you. Okay, so you do that. You can also pause at this point and then try and see if it tallies with what you have on the screen. Okay, so I'm going to clean this so we can see what we're doing next. So we've seen how we got the step you saw earlier. Okay, so now we know how we got this term here. So we need to multiply out. 3 times 3 is 9. 3 times 4i is going to give me 12i. Minus 4i times 3 is going to give me minus 12i. Minus 4 times 4 is going to give me minus 16. I times I is going to give me I squared. So that's how we got this next step here. Okay, so that's how that step came about. You can rewind and play it again if you don't understand. Take it slowly and you get it. Now that we have those values here, we simplify just like we did when we're adding. The I terms in I, collecting like terms in I, terms in I squared, and those that are real. You can see here that 9 is the only real, so 9 stays alone. Okay, and 12i, there's a step I didn't write here, so let me show you. Okay, well, anyway, so here we have 9, because it's the only one. 12i minus 12i. I have 12 naira, and I'm owing 12 naira. If I pay, I'm left with 0. Is that not so? So I have plus 0 here. And then I have minus 16. Now, I squared, everyone, please, I squared is actually minus 1. If you don't know this or remember this, you did it in secondary school. Anywhere you see I raised to power 2, the same thing as minus 1. Okay, so I squared, you see here, is same as minus 1 I have written here. So what do you have left? Definitely you get 9. That's 9 plus 0 is still 9. Minus times minus is plus. And then the 16 stays here because 16 times 1 is 16. That's how I got this place here. And if you add them together, your final answer must be 25. Okay? So that's the step that was missing there. Okay, so with that said, we're finished solving the first part where we're told to find the product. So we found this. You also need to check your lecture note. More examples are given in the lecture note. So now we're told, having found this, that we should evaluate this. Oh, well, they look almost similar, just that now the one with the minus sign is in front of the one with the positive sign. And we can see that they are the same. P and Q is 3 and 3, 4 and 4. So they're just 4, 3 and 4, and here we have P and Q. So they're similar. So if that is the case, what we see is that you can see that when we had 3, we had 3 times 3, because 3, this is the same as saying 3 raised to the power 2 plus 4 raised to the power 2. We solved it and we got this. If that is the case, and look at it, there's 3, there's 4, and there's P, there's Q. It means that this is P squared plus Q squared. So that's why we said from the solution of 3, we can conclude that the product is same as this, because they're not values. We can't find the final value. We have letters, so the only way we can do is to study and arrive at this value, as you can see there. So having said that, let's move forward. It's possible to solve this and arrive at a value. You can solve it, just multiply like we did before. Let's do that. Let's quickly show that based on that. But just studying what we've done is sufficient. But let's solve it. Let's see if we can do that. Let's solve it. So we have P plus IQ into P minus IQ. So that would be P times P, which is P squared, plus P times minus IQ, which is going to be minus PQI. And then we are through with the P multiplying, so we're going with the IQ. So IQ times P is going to give me positive IQP. And then IQ times, so there's a minus times plus, so that's a minus still. And I times I is I squared. And Q times Q is Q squared. Okay, so you have that. This and this are the same thing, because we've seen that it was commutative before. So this is a negative one, this is a positive one, so this disappears. We know I squared is minus 1, so we have P squared minus 1 Q squared. That's our next line. And what's that going to give you? That's P squared, because, and the minus times minus is plus. 1 times Q squared is Q squared. And so we've proven that this is the same. Okay? Just in case you're given to find the value directly, they might not use P and Q. They could change it to A plus IB into A minus IB. So if you're told to find this, just remember that you can multiply it as I have done here, just using your standard rule for multiplying of complex numbers. Okay. Let's move to the next example. So for the next example, we're told to simplify a quotient. This is the quotient here. To simplify this, 3i minus 2 all over I plus 2i. So the first thing you need to do, this is the question, remember? It's the same thing as multiplying by the conjugate of the numerator represented in this form. You did that in secondary school, so just multiplying by its conjugate. Now if you do that, what happens? The numerator comes together, merges together, that's what you see here. And the denominator merges together, that's what you see here. You see that? Now you know how to multiply. You simply, so what I've done is, for this solution, I separated the solutions, the numerator and the denominator separately, but you can choose to solve everything continuously. You can decide to open the bracket and keep going. but I've decided to simplify numerator first, so I'm going to solve the numerator first, and later I did the denominator. So for the numerator, which is this, you can see the same thing with this one here. Numerator, you know how to open now. You open it, get these values, you multiply them, and if you simplify, you should get this as your final answer. This value 4 plus 7i. You can pause the video at this point, try solving, see that your answers tally with mine. I then simplified my denominator, which is what you see here. Again, you can check your steps and make sure you get the value 5. I then combined my value for the numerator and my denominator. That's my denominator. Oh, denominator is 5. Didn't write it. So denominator is 5. So combining the two, you definitely will have that your value here, which is the question you were asked to solve, is going to be numerator over denominator, which is what you see on the screen here. And when you simplify further, you should get them in the real part and imaginary part as 4 over 5 plus 7i over 5. How did I get that? They both have the same denominator, so you can split them with the same denominator. So, and that's our final answer. The next example to consider is what we call finding the modulus. Again, what is modulus, if you can remember? To find the modulus, let's look backwards. I think we have it on this slide. The modulus. Okay, there it is. To find modulus, remember I said if you're told to find the modulus of a complex number, that the formula to use is the one here. This one. That's the example we're considering now. Okay, so let's look at it. So we're told to find the modulus of this complex number. The complex number is 3 minus 4i. The formula for modulus is what you see on the screen here, which is what I told you to recall. Now clearly you can see based on this formula, we need x and we need y of the complex number. Clearly your x is going to be 3 and your y will be minus 4, not 4, but minus 4, because the complex number is always of the form x plus I y. Okay, so it has to be minus 4. Okay, so that's what I've written here. In that case, x equals to 3 and y equals to minus 4. So now we want to put them in the formula for the modulus, which is this. We just substitute back. Wherever you see x, you plug in 3. Wherever you see y, you plug in minus 4, which is what you see here. Okay, but what is 3 squared? 3 squared is 9. What is minus 4 raised to the power 2? Minus times minus is plus, minus 4 into minus 4. Minus times minus is plus, and 4 times 4 is 16. We have a positive 16. Okay, that's how we got this here. So if you sum the two together, you should get 25, and the square root of 25 is 5. So that's also finding the modulus of a complex number, a given complex number. Next, we're given an equation. This is the equation you have. And you're told to find the equation basically of the circle, because if you recall, we have said a complex number represents a point on a circle with center z0, radius r. So, and it's always of the form, yeah, it's even on the screen. It's always of this form. So that's what I've told you to recall here. You can see it here. It satisfies this. And recall z0 is this here. So if I plug in z0 in here, it will look like x0 plus that, which is what you see here. Okay, so all you need to do is compare. Let me clean all my highlighting. All you need to do is compare these two together, this part first, so that you can know which one is x0 and which one is y0. You can see that? Now watch this. On the screen there you have z minus 1 plus 3i. Why the lower one is z? So if I open the bracket, I want to bring in the minus x. So I'll get minus x naught. I'm opening the bracket. And then this one, minus times plus, will be minus I y naught. So based on that, can you tell me what x is? X naught is clearly x naught. Since both of them carry a minus, it means x naught is 1. Agree? And what will be my y naught? Since this one has a minus sign and this one doesn't, it means it must be minus 3. Okay? So every time you're given a question like this and you're told to find the equation of the circle, just compare the two. This first part, don't worry about the radius part. The radius is 2, okay? So just leave it for now and just compare these two values. And then open the bracket because this minus sign is trying to enter into this. It's not entered yet. So you allow it to enter and get your expansion. You get your expansion. And then you see that the minus, sorry, this is minus here. You get this expansion. If you expand it, then you now compare the two. This will look the same, but because this one is having in this particular example, it has a positive sign, so therefore the y naught has to be minus 3 and the x naught will be 1. So that's how I got my values. So that's how I got my values that you see here. X naught equal to 1 and y naught, not just y naught equal to minus 3. Okay, so now that we know this, the actual equation we're given is this. It has 2 outside it, remember? So we want to represent this part of it, this part, which is here, like this, in its form, like this. Remember, r is 2 now in our case. Okay, so now we're just simply writing our values. We'll take this, which is what you see here, and equate to r, which is 2. Okay, so x naught is 1, so that's why you see 1 plugged here. Y naught is minus 3, that's why you see minus 3 there. Okay, so you just simplify now. So simplifying, you can see that there's a square root here and there's a 2 out here, just 2. But if you square both sides of this first part of the equation, what happens? The square root will go, okay, because root of a all squared is the same thing as a. Okay, that's what was used. Your knowledge of indices, you did that in secondary school. Okay, so you square both sides. After squaring both sides, this roof will go, the square root part will go, and this will now carry a square. That's why you see everything inside here is still here, and 2 is raised to power 2. This remained as it is, you can see here, but this part is slightly changed. Why? Because minus times minus is plus. Okay, you can see that. So it practically didn't change there for the roof, and then they simplifying for the simplification of your solution. Okay, so let's continue. So now we have this. So now we have this particular part. We understood how we got to this point. Again, first compare. Sorry, come on. Okay, let me start from the beginning because I'm practically through with the solution. Or let me finish the solution. So first, we got to this point by squaring both sides and simplifying this particular part, because this one we had nothing to do, and then you arrived at this. And simplifying further, you can break this part more than that, and 2 squared is 4. So that's how we got this, and this is the equation we seek. Okay, it's an equation of a circle centered at 1, and remember we got x not to be 1 and our y not to be -3. That's why we have it centered at 1 and -1 with radius 2 units. Okay, that's how we got that. Let me take it all over again. Let's try taking it over again. Okay, so like I said before, you compare this part and this part of the equation to get x naught and y naught. When you get x naught and y naught, you plug in your x naught, you plug in your y naught. You know your r, it's given in the equation here, it is 2. You just substitute everything back to get what you have here, right here. Okay, so after that, you simplify. First, you square both sides of this equation because you don't actually need to square the side. They are all the same thing. So you square both sides of this equation to arrive at this and simplifying the term in here. Okay, and 2 squared is 4, and this remains the same. And so we have a circle with point centered at 1 and -3 with 2 as its radius, 2 units as its radius. Okay, thank you.